Right, let me share good afternoon to all. Let me share the file now. So today I'm going to complete today's syllabus. So let me share the file which I want to. Right, so yes. Yeah, quickly, I just want to go through again a little bit. I think I thought of, quickly, go through all the basics of ESR again. Or not, look, as we all know that, yeah, good morning. Yeah, I can see how many students are there now. Only 10. Okay, it's okay. I think we may join. So the main, suppose if they ask question related to like explain the ESR spectroscopy. So you should know the first what is ESR, what is the theory behind that, and then you have to explain what are the equipment like instrumentation, like what are the equipment required to test the organic sample. Like you need to know the working actually how it works. So these are the steps you have to suppose. Even if they ask long answer, you should have these side headings. Then spectrum, what is a hyperfine splitting, and what is actually lambda factor and applications. So I mean, I don't want to spend much on this, which we have already completed. Okay, but let me. Okay, so yes, it's basically very very it is a one of the spectroscopy technique which actually gives the information about the electronic energy states, how they go from one state to another state in the presence of magnetic field and microwave frequency. There, when they match together, you have the resonance. So the splitting of like basically splitting of line in the presence of magnetic field we call a G-man. But if you want to see resonance, definitely you need a microwaves which actually makes the spin of electron to spliff into the other direction to have the resonance. Okay. So the approximate microwave frequency is about like 10 power 4 to 10 power 6 that you have to keep in mind. And you also need to know that what actually ESR phenomenon. So we apply only for, we all know that it should have the valency electron, unpaired electron, right? So it should have a unpaired electron, okay, and it should have the atoms which are having odd number of electrons also. It should be you can see here odd number of electrons also. Um, yes, having odd number of atoms also shows this peak. And however, like even the ions which are having the partly filled, which means they have the inner electrons, like the valence electrons. I mean, free radicals also you can see the spectrum. So we should keep in mind odd number of electrons and unpaired electrons, like even free radical like CH3 like that. These are the atom which actually shows the ESR spectroscopy. We also call this EPR spectroscopy. Why? Because we are dealing with the unpaired electrons, which means paramagnetic substances. So that is the reason we call it electron magnetic resonance or electron paramagnetic resonance. So EPR, EMR, ESR. There are three names there you should keep in mind. So the paramagnetic substances are those which basically requirement is valency electron or unpaired electron. The examples which we already discussed, oxygen, NO2, NO, unstable paramagnetic substances or free radicals also shows the ESR spectroscopy. What is the theory behind this actually? The theory behind that, you know that energy levels, the electronic level, the energy levels can be changed when you apply the resonance condition. What is the condition? When we can see the resonance condition? Only when you apply the microwave frequency to the sample. So whenever you apply the microwave frequency to the sample, so basically there you have the magnetic field as well as the microwave field. So both will match and you have a resonance. Like basically the spin of electron would change suddenly. So such condition we call it as a electron spin resonance. Okay, so uh, electron spin resonance spectrum can result what? It gives the information about the transition between the energy level. How? By observing the microwave frequency. So they do shows the spectrum only when by observing the frequency of microwave. When they observe the frequency of microwave, they do have the transition. They do have a transition between the energy levels, like plus or minus. So as we all know that electron has a spin, which actually, because of that, in the presence of magnetic field, it split into the two levels, which actually G and Fn. But again, we are applying the external frequency, which causes the resonance condition. So you should know that resonance condition. Okay. Yes. Again, you should know that because of the unpaired electron only we could able to see the resonance, and excited electron changes its direction of the spin. So when you apply the frequency, immediately what happened? Whatever electron, excited electron, they change into direction and reaches the ground by emitting the energy. Okay, so that would be happen transition between the two different energy levels by observing the quantum energy, which is h nu, but the frequency should be in the range of microwaves. So microwave absorption is measured as a function of the magnetic field. You can able to see this, but here keep in mind magnetic field we are keeping the constant. You can clearly see in here, this is the here we don't apply any field, right? So here you can have the spin of electron which has a 2 plus or minus of, but when you apply the field, there is an energy gap between them, right? So what is energy gap? They split into energy different levels, plus half level, minus half level. Plus half is always higher energy state with having energy mu h. So even the other is minus mu h. But the gap should be, energy gap should be difference of E2 minus E1. That gives the 2 mu h, which is also equal to the h nu that is applied to this sample, like microwave frequency energy. So, I mean, these are the transition, possible transition happen. Okay. And how that also can be written as an equation 2mh magnetization into h, which is equal to h nu. This is a absorption frequency or absorption energy. Okay. And nu is the frequency. The energy can be also written as h nu is equal to g is a lambda factor, b is a field, and h is the apply intensity. So here beta, not B, no, G beta H. So G beta H, beta is a Bohr magneton, EH by, it's a very important, keep in mind this. Beta, we call it as beta, which is a value of EH by 4 pi m, and G is the Landau factor, which is also given, actually can also get that value, is about 2, but it can be varied. H is applied field. So you need a applied field, and the Bohr magneton can be calculated based on electron charge, Planck constant, mass, etc. Okay. So the what are actually devices that we need? What are actually parts of the experimental setup? We already seen yesterday. The first one is we need a source, right? What is the source name? Klystron. What is a klystron? Which actually produce the microwaves. The second one is actually isolator. So as we all know that the klystron produce the microwaves, but this isolator can actually help to make the like strip up, like it just make the small, like you can think about it like a single, I would say, like a single wave frequency. So isolated is a kind of strip of para. It's a material is made by isolated is ferrite material, but it gives actually like very fine frequency. Okay, and you have a wave meter also. It can actually basically calibrated with the device. Wave meter can actually what is the wavelength, what is the field, which actually calibrated. And attenuator also, like there is a attenuator which actually the noise can be observed, whatever noise is happen, which actually observed by the attenuator. So this is a very important, I mean, this can also be used. It process basically absorption element and whatever the other signal is there. Okay, and the other one, we already know that the sample, you can see that this is a sample, right? Sample cavity, the sample cavity where you are keeping the basically sample, whatever sample which has having the unpaired electron. Okay, so we have discussed clustron, sample cavity. Okay, and crystal detector. So detector should be here. The crystal detector, it could be here, which is actually made from the single silicon crystal, which basically act like a microwave rectifier. Rectifier means it increase the signals basically. And you can also have the basically oscilloscope. We all know that oscilloscope, where you could able to see the signal. Okay, and the magnetic system means basically how much magnetic field you can apply. That is what you can keep it. How it works? The cluster basically set up. First, we need to set it. You need to turn on and to produce the microwave. Then after that, what happened? It passes through the isolator, attenuator, etc. Then it passes through the sample. Then the magnetic field also passes through the sample. Then detector can actually identify the number of whatever signals which due to the unpaired electrons. Okay, so here you can have the basically you apply the microwave frequency, you also apply the field. So at certain conditions, whenever you have the both are same frequency, you have the resonance, right? So at that time there is a sudden peak in the detector. So that gives the information like this. So this is a peak of resonance peak. So the intensity versus magnetic field. So at this point, you have a maximum peak, and that can also be when you do the derivative of this peak. So you are going to get this one. So let's say someone asks you, what happens, sir? Like if I get this peak, what I can do that? So with this peak, if you calculate the area under the peak, what it gives actually, the area under this curve is directly proportional to the number of unpaired electron in the sample. So that information is really wonderful, right? If you know that, you can do a lot of characterization. Like you can know the structural information of the material. So that is a very good information, right? And in order to find out the number of electron in unknown sample, and this is a very good technique to give that information, unpaired. So mostly widely used standard samples like this, they compare the with respect to the standard sample, whatever the unknown sample, also you can get the information of unpaired electron. So now you understand that whatever the signal, whatever the peak you get it, in the under the peak you have to calculate the area. There what happened, that area is directly proportional to the number of unpaired electrons in that sample. So this is the last topic of this unit, hyperfine splitting. Hyperfine, what is a hyperfine? Hyperfine is after splitting, again they split into the, so it's like an interaction between the nuclear magnetic resonance. So as we know that hyperfine structure is nothing but, it's like a chemical shift in the NMR, similar to the chemical shift in the NMR. So hyperfine is basically electron interaction between electron with nucleus. So that gives the hyperfine structure. So whenever you have an interaction between the nucleus and electrons, then you have a hyperfine structure. Again, they split into, so first actually in the absence of field, you have the plus of minus of, again whatever plus of is, again it's split into the plus of minus of, here minus of again split into the plus of minus. So that is a hyperfine. So after splitting of, again they split into the 2 level. That is called hyperfine signal. It is caused by what? Spinning of electron, and there is basically you have electrons, and adjacent to there is a spinning of magnetic field also. So whenever you have a magnetic field which also basically curly, right? So it is a like you all know that magnetic field spin it always, it helps to torque. There is a torque, right? Whenever you have a magnetic variable magnetic field, there is a curling, actually torque happen. So with that, actually whenever the electron interact with this curve, you have that hyperfine structure. So when a single electron is interact with the one nucleus, the number of splitting will be 2a. How many splitting? This you have to keep in mind. So how many splitting will be? Suppose L is a spin quantum number. L is half. If I keep L is half, 2s plus 1. So S is half. So in that case, 2 levels, plus half, minus half. Okay. So you should keep in mind. So in general, single electron interact with the magnetic field with a n equivalent nuclei. The electron signal is split into the 2nl plus 1. In general, 2l plus 1, 2nl plus 1, you should keep in mind. 2nl plus 1. L is actually spin quantum number. N is a basically is nuclei, number of electrons. N is the number of unpaired electron. N is a number of unpaired electron. L is a spin plus 1 for the multiply. Let us see that how it happened. So you should keep in mind, Anna, this is the, let's say you have a ground state in the absence of let's even you can see the 2 levels also in the presence of magnetic field, but they split into the plus half and minus half, right? In the, when you increase the field, you have this condition, plus half, minus half. Minus half is a low energy state, plus half is higher energy state. Then again, hyperfine structure means you are basically, there is an interaction between the electrons and nucleus. So in that case, again this plus half, again what happened? Split into the plus half and minus half. Again minus half also split into the minus half, plus half. Keep in mind, plus means higher energy plus, minus means minus is higher. So now these are the possible hyperfine coupling. Hyperfine, and there are 2 peaks. There are 2 possible peaks. How you should apply this basic selection rule. So you may have a question. Selection rule means, what is actually selection rule, sir? So here you can see, Nana, first transition to happen this. So one transition should be minus half to minus half to minus half. Change in should be 0, right? So the hyperfine condition should be 0. Change in so minus half of minus half is 0. The other one is plus half to plus half. This is a very, very transition between the hyperfine structures. The condition is delta mi equal to 0. So the possible transition should be only minus half to minus half, plus half to plus half. But whereas here, it's not like that. So plus half to minus half transition should be there. The condition should be plus or minus half. Okay. So plus half minus half means it's going to be 1 actually. Okay. So to happen here, transition is, the condition is plus or minus 1. To happen here, condition is plus or minus 0. So you should keep in mind, this is a compulsory question for the competitive exam. Selection rule for hyperfine structure is delta mi 0, whereas the normal Zeeman effect condition is plus or minus 1. And there are 2 possible, you can clearly see that. So as I mentioned yesterday, I just want to show you how to, that syllabus is over now. So far it's over, but I want to explain you what is actually G factor. ESR spectrum also talks about the G factor. So the best method of measuring of the G value is basically, measuring the spectrum, whatever spectrum from ESR, then you get directly from this experiment. Actually, you can also get value of G value, but how do you calculate the question? So I'm going to show that how do we calculate it. I think this I'm not going to explain here because I have already explained this both NMR. Sometimes they ask what is the differences between AMR and ESR. You can just, I'll post anyway this PowerPoint presentation in the group, so you can just read it. I mean, we have done both and just comparison. I'm going to applications of ESR. So basically, what are the applications? Study of free radical, unpaired electrons. Basically, we are going to study the three, at least you can keep in mind few of them. One is free radical. You can also identify the unpaired electron. It can also helps to determine the structural information, right? So at least, structure of organic, inorganic, free radicals also can able to get from the ESR, right? So all these possibilities are there. You can read it. I'm going to show some example, real example. So we have done just now, shown this one, right? In the absence of field, plus or minus 1, but when you apply the field, plus of minus of, the condition when you apply the plus or minus selection rule, you have this transition. But to have the hyperfine structure transition, only it should be plus or minus 0, because change in plus of to minus, plus of to plus of is 0, minus of to minus of also 0. So that you should keep in mind, all of you. Okay, is it clear? So the change spin should be 0. That is condition for the hyperfine. If the change from like plus up to minus change is equal to plus or minus 1, that is normal transition. So there are some example I took it here, like oxygen. What happened for oxygen? Let us say the possible states you can see here. I is equal to half. I should be, you can take 1. The possible MIs are plus 1, 0, minus 1. If I take I 3 by 2, possible MI values are like this. If I take 5 by 2, you all know this. I think I have given the like plus MI2 minus ML. So you can have all possible values. Let us take oxygen. Oxygen is, let's say, if I take 0, so what happened? This entire thing is states become only one peak. This is going to be 0 plus 1. So total is one peak only. You can collect only one peak in the ESR. Similarly, hydrogen atom. Hydrogen atom, let us say we all know that 1 electron, right? How many electrons there? 1 electron. I is, let's say, nuclear spin is half. What are the condition here? 2NLL, 2NL plus 1. 2 into N is actually what? Number of electron 1. Okay. Oh, we are almost okay. Number of, okay. Let me clear. So N is actually, we know that 1. Nuclear spin is half. So how many levels you have? 2 level. So for hydrogen atom, you have a 2 ESR spectrum. Similarly, radical also, CH3. So you can have the, so even you can see here for CH3, I 3 by 2, 2NLM plus, you have here three hydrogens are there. So 2 into 3 plus into half, nuclear spin half, plus 4 lines you will get it. For CH3, basically, you gonna end it with 4 line spectra. For hydrogen, 2, oxygen, 1. So all this may ask in the exams. So this is the spectral term. I think I have asked the question yesterday, no one answered. I thought of it's good to this compulsory question in all gates, CSR, etc. So I'm going to explain like within 2 minutes. This is the, all of you note down this spectral term indication. How do we indicate it? N, 2s plus 1, L, J. N, again, write all of you. N, 2s plus 1, L, J. This is a spectral term. We call it as a spectral term. What is the N? N is a state. 2s plus 1 is the, S is a spin. Okay, this is also called multiplicity. 2s plus, what do you call it? 2s plus 1? Multiplicity. Very, very important. If spin is off, what is the multiplicity? 2. If spin is 3 by 2, multiplicity is 4. If spin is 0, s is 0, then what is going to be multiplicity? If s is 0, 1. Okay. So now let me take boron. Boron, actually, let us say, what are the, how do we write this? Spectral term is 2p. I'm going to write p. So p means for p orbital, what is L value, beta? Its L value is basically, L value is how much? 1. For s orbital, L value is 0. So if I give the spin is off, because in the p orbital only one electron there, so spin off, so 2s plus 1. 2s, if I keep spin off because one electron is there, okay, then it's going to be 2s plus 1, so that is going to be 2. So L is what actually? L is actually orbital, total angular, orbital angular momentum. So orbital can be p or l. It depends upon if for basically 2p, right? So basically it's a p. L value is 1 for the p orbital. L value is 1 for the p orbital. So, but how about J? J could be L plus or minus. You can also see here. J is actually L plus S. Okay, L plus S. So here L is 0. L is 0. N is equal to 1 level. So in that case, you are ended with S only. Off. Here off. Okay. So you can practice more. You can. I have also given here S1, D1, P3. So for this, multiplicity is how much? S is actually 2s plus 1 is equal to 1. S is equal to how much it is? I think if I keep 2s plus 1 is equal to 1, 1 and 1 cancel, S is equal to 0. So spin is 0. So for S value is actually, S orbital L value is how much? 0. L is also 0. S0, L0, then both are 0 means J0. Okay. For first one, simply you can say S0, L0, J0. For second one, you can say, okay, second one again 2s plus 1 is equal to 1. So S is equal to 0. But D is how much? L value is 2. For D orbital L is equal to 2. J is what happened? L plus J. So again 2. So you should know how to calculate the spectral terms, and it's very, very important. So then okay. Then again another one is Landau factor. This is the formula for Landau factor. Yesterday I was trying to explain it, but no one answered it. So G's formula is, you keep in mind all of you, 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 and by 2J into J plus 1. So for a given this spectral term, they will ask you to calculate Landau factor. So for this, 2s plus 1 is equal to 3, S is equal to 1, J is equal to 1 because this J is 1, L is equal, when J is 1, S is 1, so definitely L plus S means L is equal to 0. Why? Because S orbital L is equal to 0. So now you know all these three. So 1 plus 1 into 1 plus 2. Now if you calculate it, you are ended with the G value is 2. Similarly, you can do anything, even fluorine 6 off. So here S is equal to how much? How do you calculate it? 2s plus 1 is equal to 6, right? 2s plus 1 is equal to 6. So 2s is equal to 5, right? S is equal to 5 by 2. So not fluorine, sorry, F orbital L value how much? 3. S orbital L value 0. P orbital L value 1. D orbital L value 2. F orbital L value 3. So when you know these two, J, how do we get it? L plus S. You can get the J value. Then G factor, you will get it. Similarly, you can calculate other elements also, other spectral terms. I think this is what I want to, complete it today. If you have any questions, please let me know. Any questions? Students? Yes, any questions? Sweta?
No, sir.
I mean, did you understand this Landau factor now?
Yes, sir.
Landau factor and spectral terms are very, very important. Two questions, direct questions again. Actually. So very, very important. Just practice more. Even Google it. Some questions like,
Okay.
calculating the Landau factor, calculate spectral terms. There are a lot of questions are there. Okay.
Okay, sir.
So I think we have done like ESR, NMR with problems, everything. Hope you understand well. I'm hoping that my question, whatever question come in the exam, definitely 100% all of you are going to attempt it. That is what my contribution. If you are not going to attempt my question, that means I am failed to teach you guys. Just if you have any questions, definitely I will help you. But try to understand. Just go through all the slides and make your own notes. I think that's enough. I mean, whatever slides are there, that's enough. I think all theory is there. You just need to make your own notes. Like if they ask long answer, what should you do? If they ask 5 marks, what you have to do. But competitive purpose, I think 100% I have covered it. For exam purpose also, I think it helps a lot. Any question from anyone still? Sushma, Veena, Anusha, Ashwini.
No, no, sir.
Uh, Satvik. Okay, but others they did not join. I don't know why they did not join. The people who are in the DRDO, yeah, today is working day, right? I think yes. I think they are there. Okay.
Yes, sir.
Okay. Okay. That's good. But anyway, thank you for joining my class. Even holiday, I thought of like when I decide I want to finish it. That's why I always think about it. I don't want to postpone anything. So I have planned before. So I have completed. So my task is over. All the best for you all. Okay. Thank you so much. Have a nice day, beta. Have a nice day. Thank you.